Uh, Hello, everyone. My name is Gautham Shenoy, and I'm from AMD. And the first talk, so there are two talks, sorry about that, but the first talk is on some odd behaviors that we've seen with a couple of workloads and how we tried to push back and then what we did in order to address some of these problems. So this is work that was jointly done with my colleague Pratik Nayak, who couldn't be here. So like I mentioned, this is basically a tale of two workloads. So the first one was a curious case of lost throughput and a drastic loss of throughput on one of the SPECjbb 2015 configurations. And we observed a very large regression when the workload team moved from 5.7 to 5.13. Everything else was the same. The stack was entirely the same. The hardware was the same. The firmware was the same. It's just that the kernel just changed, and they saw a 30% slump. And we kept on pushing them, saying that, go to a more recent kernel, because we've added these awesome features. Vincent has added, load balancing magic there to make things better. And they took our advice, and then they came back and said, well, it's really not working for us, right? And the other tale is kind of on the other end of the spectrum, where this is benchmark called DeathStar Bench, which mimics microservices, running on the same server. And we were hoping that, as we increase more and more number of DeathStar Bench instances, we will see some scale up, but scale up was nearly not to be found. And when we did some debugging, we originally thought this may be, some hardware issue, but it turned out it was not. There is still a little bit of a shortcoming in the Linux scheduler that we could address to get better performance. So let's get started with the first one. Now, SPECjbb 2015. I hope, in case you don't know about it, this is one of the benchmarks in the spec suite. A lot of customers ask for these numbers when they evaluate platforms. So it's important. AMD is a silicon company. It's important that we get good numbers on this. So the workload team makes sure that they try to tune it to an extent possible to extract the best possible numbers for the two metrics that this measures, called max jobs and critical jobs. Now, the metrics are measured by varying the load on the system, and we'll see in the next slide what they exactly are. And the workload can auto scale depending on current responsiveness. So they can spawn more threads, allocate more memory, but the system administrator is allowed to put a cap and say that you are not allowed to use more than so many threads and stuff like that. And the configuration that we were looking at is a multi-JVM configuration, where each JVM is pinned to an LLC. So on the AMD EPYC 3rd generation server, LLC happens to be a chiplet consisting of 8 cores. That's where they share the L3 cache, and the socket consists of 8 such LLCs. So they were all pinned to separate ones, so there is no chance of these things escaping, the LLC. So we thought, this may not be a scheduler problem, but we'll see. So coming back to the metrics, so there are two metrics, like I mentioned, max jobs and critical jobs. Max jobs is something like they keep increasing the load on system, and they measure the maximum throughput that they get before a failure. The failure is defined as the inability to meet the SLAs consecutively. So if you fail to meet a SLA and then you're able to meet the SLA the next time, that's not really considered to be a failure. So you get to a point where you fail back to back, and the maximum throughput you got until that point is the max jobs. And the critical jobs is basically latency constrained throughput measurement. They measure the transactions that finished at different intervals, I think 10 milliseconds, 25 milliseconds, 50 milliseconds, 75 milliseconds, and 100 milliseconds. And then they take a geometric mean of that, and they present this as the critical job. So these are the two metrics that this particular benchmark cares about. And so being a silicon company, the workload team tries to keep the software stack constant for a long time, because they are trying to evaluate changes in the firmware, changes in the microcode, and stuff like that. So, and they once in a while they go to a more recent kernel. So we've prodded them to reduce that period and go to recent kernel more often. But like I mentioned, the drawback of this methodology is that you could have fixes or enhancements in the upstream kernel, which they probably are not aware of. And a lot of times what happens is, and it has happened in the past, that they came back to us with problems saying that this is not working, but then there was a problem that was fixed upstream. So we just had to tell them, go to a more recent kernel and the problem should be fixed for you. So similar thing happened. We asked them to go to a more recent kernel. They did. They went from 5.7 to 5.13, and they came back saying that our max jobs dropped by 20%. So everything else was the same. They came back to us and said, what's the problem? I mean, you are supposed to be better. Why did the throughput degrade? So one option was to do a git bisect. Now, each run of the workload takes 2 hours. And between 5.7 to 5.13, there are 7 to 8 intermediate release candidates. I think we counted it was 13 bisection steps. So it was going to take 50 hours. We started that. It landed on a merge commit. So we had to do further refinement to see what the bad patch or bad commit was. But in the meanwhile, we just thought, we don't know whether the problem is really in the scheduler, but let's give it a try. Let's just ask them to capture proc shed stats before and after their entire run and see what the behavior is. And when we did that, we observed that there is a problem. There is a significant difference in the shared stats. For instance, you could see that the number of times the schedule was called was 20% higher on 5.13 compared to 5.7. The edge set was kept to the same. We measured that was not the case. Try to wake up was not so much difference, but the number of context switches was significantly higher on 5.13. Okay, so there may be something to do with the scheduler. We went further and looked at the load balancing statistics. And one interesting thing that stood out was how often do we pick cache hot tasks, right? And we saw that in 5.7, we were actually pulling these cache hot tasks, which is basically a task which ran recently, and we are not supposed to ideally pick that. But if there is a lot of pressure, we do end up, picking it and moving it for getting the load balance right. But on 5.13, it was 0, right? So we are not moving any cache hot tasks. So what's happening really? Looked at the code, and you see that the thing that determines whether a task is cache hot or not is this particular tunable. I don't know whether I should be calling it a tunable, called sysctl shed migration cost. Now, this is one of the debug tunables, and it basically gates and determines whether you can call a task hot or not, which determines whether a task can be pulled or not. So we were wondering, I mean, wait a minute, are these guys modifying the scheduler debug tunables that we were not aware of? And turns out that they were. What changed in 5.13? Things that were there in proc sys kernel shed star moved to sys kernel debug. So we had moved these undocumented debug tunables from procfs, which previously was modifiable through sysctl, to debugfs. And the runner scripts were using them. So we went back to the workload team and said, why are you using them? These are not meant to be used in production. And they were like, well, the Java tuning guides have always recommended modifying them. And we looked around and it was true. I mean, both Intel and AMD, the Java tuning guides mentioned that you need to write some values to these tunables to get real good performance on multi-thread workloads. All right, so as a result, when the location of the tunables moved, the performance went down because there was no files to write to anymore. All right, so we said, okay, let's modify your scripts. Let's see if we get the same performance back when we write to the debug thing. And yes, it did. So we knew that this was the problem. And they were very happy. Hey, thank you very much. You guys fixed our problem. But we were like, no, you're not supposed to do that. Did you not get the message? The reason why these have been moved away from proc sys kernel to debugfs is these are meant to understand. It's meant for us scheduler developers. It's not meant for you guys. And so what we realized is, I mean, we do advocate folks to not use them, but whether we like it or not, and whether it's knowingly or unknowingly, or whether it's wise or otherwise, people do end up using it in production, and we have to debug these problems. So So what were the tunables that were used? So in the script, we saw they were using min granularity ns, which determines, once a task gets onto the CPU, what is the minimum amount of time it gets to run, modulo somebody else doesn't wake it up because of wake up granularity. Now, wake up granularity is basically the amount of buffer that is given for a newly woken up task, before it can preempt the currently running task. Then you have the migration cost ns, which, as I mentioned, determines whether the task is hot or not. And then you have, I think, the NR migrate, which determines how many tasks do you migrate, in one shot while you're doing load balancing, and a whole bunch of this. So we enable them one at a time, because first thing we told them is we are not going to, we should not be using them. So they got back to us and said, fine, we are not going to use them, but please give us a recipe without using these tunables. How can we recover the same performance that we have been used to so far? Okay, we said, okay, let's try to find out what the issue is here. And we enabled one at a time. And what we understood is that the maximum performance gain was they were obtaining by only modifying wake-up granularity, which basically is saying that, by increasing the wake-up granularity whenever a task wakes up, don't preempt the current running task. Let the current running task run for a while. So you're increasing that buffer period. The next thing that really helped them was the min granularity. And the other two things that helped were the migration cost and the NR migrate, but these were primarily to recover the critical jobs. For max jobs, the first two are enough. That is, min granularity and wake-up granularity were more than sufficient to recover the max jobs. It was only to make sure that the critical jobs did not regress that we had to consider these other things. So now we don't want them to use it, but we should at least try and understand why is it that these tunables are giving them benefit, right? I mean, at least that's something that we owe them. So when we looked at the values that folks were setting to these tunables, and these are crazy values. I mean, extremely high values. Like, I don't even want to name them. It's atrocious, and some of them are not even consistent. Like, for instance, you have min granularity ns set to 250x. And latency ns just set to 1.5x, which doesn't make sense. Min granularity ns is supposed to be smaller than latency ns, but the interface is such that you can write whatever you want into these interfaces, and people have been doing that, right? So then we went back to them and said, how did you guys use these values? I mean, can you please tell us who told you to use these values? And they were like, we have inherited these values from some time ago. And when we prodded them further, this was really their intention. So what they wanted to do really was, to reduce the number of involuntary context switches. They wanted to reduce the preemptions that were happening in the transaction part. That was their main objective here. They wanted the processing to run, for a longer duration so that a transaction is not interrupted in the middle. And to achieve this, they increased the min granularity and the wake-up granularity. And what about the other two? Well, if you increase the min granularity and the wake-up granularity, what happens is a newly woken up task now gets piled onto the run queue, and it's not going to run fast enough. And that may hamper your critical jobs. So which is why, to mitigate that, they reduced the migration cost so that these can be aggressively pulled on to other run queues. And also the NR migrate, so they can pull more of them, in one load balancing iteration. So this was really their intention to do that. I mean, that is really what they wanted to do. And there are different types of SPECjbb threads. There are these transaction injectors which inject these transactions. There are these backend threads which are supposed to process these transactions. And these backend threads, they sort of interact with this fork join pool, which can create threads on demand. And there are multiple triads of that. Then there is a map reducer, which acts as sort of a medium of communication between transaction and backend threads. So there are these different types of SPECjbb threads. And then we thought, okay, let's try and understand what is it that it's really changing. And it was quite obvious. So you see that when you add all these tunables that they had added, the average atom, which is the average amount of time that a task runs on the CPU before it's kicked out, it was up by 19%, 14%, 21%, 23%, 20%, and so on. But the wait time also increased. I mean, you could see that for the backend threads, the average wait time did go up by about 281%. And the involuntary context switches came down drastically. The migrations went up drastically. So all of this was like confirming what they intended to do and what was happening in the system. So this part was fine. Curiously, the number of active threads, that this workload was spawning in these two different configurations was different. So when you add these tunables, the number of active threads go down. So the workload would not spawn as many because it's seeing progress being made, so it doesn't feel the need to do a spawn more thing. And I don't know whether that was helping or not. So then we looked at, is there anything on the cache side that can help us figure out? And if you look at the total accesses per second, it was going up. I mean, it was going up by 13.31%. And fills from L2 or fills from L2 or L3 from the local LLC was also going up. But the remote cache accesses was going down with this particular configuration. So somehow, getting that particular task, some of these tasks to run for a longer duration was helping the workload on this particular architecture. So this is what we gathered at this point. Okay, so now we know their intention. Can we at least try to replicate it with the standard interfaces that we have? We don't want to touch the tunables, debug tunables, but we want to at least see if we can recover the performance using some standard interfaces. So we spent quite a bit of time trying to figure out what are the nice values that we need to set to what class of tasks. And we had back and forth between the workload team. And what they suggested were the really critical ones are the backend and the fork join threads. And what gave us the best performance was setting the nice value of -20 to these, while setting the value of +19 to the others. Now we tried setting the value of 0, the normal nice values to others, but it didn't give us as good a performance. This one did. And by how much? So we saw that we were able to recover the max jobs by 1.25x. So there was still a gap of 5, but we were not able to keep the critical jobs same. So we were still seeing that the critical jobs was dropping. And this is probably some more permutations and combinations of these nice values, but it's honestly painful. We spent quite a bit of effort on this, and this is the best we could go with the nice values. So any thoughts, any insights on what could have been tried? What else could have been tried? And I mean, when we looked at the scheduler statistics, we saw that with these nice values, the average atom time was not as high as what it would have been with the tunables. In fact, it was lower for the backend threads. However, for the fork join pool, it was more or less the same. So we still have to understand whether that is the critical part. And we also saw that the involuntary context switches were higher compared to the tunables, which was to be expected.
Gautham, can you hear me?
Yes.
Okay. Did you try SCHED batch?
We tried SCHED batch. So what used to happen when we did SCHED batch was all the other tasks which would run at the non-batch priority would end up still preempting them. So we did not, I mean, when we selectively tried SCHED batch for all the other tasks which were not as important, it still did not give us the throughput as we have got with the nice values.
Okay.
Yeah. I can probably repeat the question. Yeah. Yeah. Mm-hmm. Okay. Okay. I'll anyway, we have queued it up. We are trying it out as we speak. So the question was, okay, the comment was that the older SCH bench, so Chris Mason just made a comment that the older SCH bench wouldn't have shown any difference with the longer time slices, but the latest version that he posted yesterday, it was posted to the mailing list, that does have an impact. So we can probably use that to model some of this behavior. So then we thought we'll just go to the other extreme, and this was not meant to suggest, this was to see whether we can still recover some performance, right? So we have these other scheduling classes that we tried out, and Shed FIFO was a bad idea, so we didn't even bother trying that. And we went to Shed RR, and we played with the period, which is the time slice that we are allowed, and we got the best results for 500 milliseconds. But even here, what you see is that with targeted Shed RR, where you just set these backend threads and fork join pool threads to Shed RR, and the rest of them were just Shed FIFO. Sorry, Shed other. You could only go up till 1.24x, and there was even further drop in the critical jobs. And the further drop was because if you see the average wait time for backend and fork join pool, because they were on the same CCX or the same run queue, they would have to essentially wait behind each other. If one of them is running on the CPU and the other one is ready to run, they would essentially have to wait till the other guy finishes the time slice, and that was just blowing up the average wait time. So this was not good enough. When EEVDF came out, we tried on that one as well, and actually without modifying the base slice or without adding any nice values, the default EEVDF gave us 1.17x of what the vanilla kernel was giving, and it was able to push up the critical jobs, to 0.94x. So there was just a 6% drop. But overall, from our experiment so far, it's just been the targeted nice that has given us the best results if we don't consider the debug tunables. And really, I mean, this is the problem that I mentioned with the tunables, right? Even though we are seeing this, sorry.
Yeah, so EVDF is very preempt happy at the moment. That's one of the things I still need to look at. Hopefully Thursday after the conference. But yeah, it's incredibly preempt happy.
Yeah, we've not been able to explore more with the by modifying the base slices, Peter. So Prateek is still running some tests around that. So we should hopefully have some results. Yeah.
There's definitely some code missing there. It preempts whenever it possibly can, and as eager as it can. So yeah, it needs to be tamed a wee bit. But I'll look at it at the end of the week.
Okay. Yeah. So yeah, we still, and we have not yet played with the nice values and the latency nice values. So that's still not done for EEVDF. And then I mean, it may seem that probably we need to look at reintroducing tunables, and there was like an ask from the workload team after 6 months of us exploring these things that why don't you guys just bring back the tunables? I mean, what's wrong with that? And this is really the problem, right? So even though each of these tunables are independently, you can write a value independently to it, there is really an interrelationship between some of them. Some of them end up constraining the others. So that is not really obvious to the end user. And that is one thing. The other thing is really, it really depends on the machine, and it really depends on the kind of workload that you're running as to what is it that you're setting these tunables to. And you really have to do this trial and error. And I'm not sure whether that's the right way to go forward, right? So,
and it's machine specific. I mean, these tunables are machine wide. So if you run two workloads, even separated by partition, they're both affected. So yeah, you'd ideally want to model in a task model. But yeah, the whole non-preempt thing is incredibly difficult, because even if your tasks do not want to be preempted, if there's other tasks, for example, you're also doing an MP3 player or streaming a movie or whatever, they really need that preemption. So if you combine these different workloads, it's hard. But yeah, we should perhaps do better. But if you also look at the EEVDF patch, it basically removes a whole bunch of the knobs that they were tinkering with.
right.
So bringing those back is a bad idea in many ways.
That's precisely the next slide. I mean,
okay, fair enough.
Yeah, we are getting rid of a whole bunch of them. I mean, we just have what used to be the min granularity being now redefined as the base slice in EEVDF. So we don't even have those other set of tunables, which I think is the right way to go. But yeah, so the question really is, now that we have explored these existing options and we kind of understand what was the intention of the user to set those atrociously high values to the tunables, is there a more principled approach for us, for the users, to communicate that to the scheduler? Like something like, when a task gets to run, it can run for a certain duration without getting preempted. This need not be a guarantee. I'm not saying that we have to guarantee this. It's not like a hard real-time requirement or something like that. It's not. It can be satisfied on a best effort basis. And then other requirement could be that once a task is ready to run, it probably, in these cases, it doesn't mind waiting as long as the period of waiting is really, bounded. So is this something that can be done using existing interfaces that perhaps I have not explored? Is something like deadline that we should try exploring here for this, or do we need?
Yeah, so with deadline, you're currently missing that demotion to sched other that got mentioned earlier in the day as well, perhaps yesterday, I can't quite remember. Because with deadline, if you run out of slice, you're dead. I mean, you're just blocked, and that's not typically something you want to have happen, because this is definitely an overcommit situation. So there's things. I'm not sure if there is much sensible things to do with CFS as it is today. But with, for example, EEVDF, you could expose the request size directly instead of through latency nice. But yeah, I still need to see what we do with the preemptions. Like I just mentioned, if you have a MP3 play of whatever YouTube, that definitely does want to preempt your very long-running critical job thingy. So there's fundamentally nothing you can do about getting preempted unless all the tasks in your partition, which might be the whole machine, are cooperating on that. But yeah, we should definitely explore what options there are to express these things. I don't have a problem with that.
Yeah. So yeah. That's probably the question that even I had. Like, what are the potential interfaces, or perhaps to EEDF, right? So is there any other way of providing the latency nice hint rather than abstract numbers? I don't know. I mean, this is just open questions. So. So any other comments? All right. So this was the first story. We just finished one tale, and now we are going to look at the polar opposite. So we just right now looked at a monolithic workload where things like to run for really long. Now on the other hand, you have something like this, a messy graph of services interacting with each other, talking to each other. You don't know which one is going to wake up whom, and they run all of this on the same box. So this is the diagram of a microservice benchmark called as DeathStar Bench, which sort of simulates a user timeline in a social networking service. This has a really, really complicated flow, but what you're focusing on in this part of the talk is just a relatively simple flow, which consists of the client sending a request, which is hand-fielded by the load balancer, which directs it to Nginx, which then redirects it to something called as a read home timeline service, which models the timeline, and then that interacts with the Redis and the post storage. So, and then once the data is obtained, it is sent back. So you have that kind of a flow here. And this is based on an ASPLOS 19 paper. So the motivation for our workload team was to kind of see what is the best case throughput that is possible when all the services are within the same server and they're communicating with each other, and to see how well we scale. Like if we increase the number of instances, do we see a similar linear increase in the throughput as well? because one of the things that they were concerned about was that because we have this chiplet kind of an architecture where you have L3, which is split across the chiplets of the socket, if as we increase the number of instances, will we see a lot of cache-related things that will bring down the throughput. And when they saw that the throughput was not as scaling, they initially thought that was really the problem. But when they were observing, when they moved from one LLC to two LLCs, this is one instance to two instances, one of the patterns that they noticed was that there was something like a cyclical pattern where if you observe top, all the cores on one CCX or one LLC has all the high utilization. The others are completely idle. And after a while, that thing just shifts. And all of them are now running there. And this is like a dance that's happening. So effectively, you're not using, even though you've provided two LLCs, it's just that one is being used all the time. And this basically made them wonder if there is something that they're missing in the scheduler. So out of curiosity, we just asked them, hey, why don't you guys just run with config SCHED MC disabled? I mean, this was just out of, it was just a humorous suggestion. And they came back and said that, well, you know what, that actually helps. And this was surprising because here you have a kind of a workload where you have something like a producer and a consumer where services are talking to each other. And one would think that it would be ideal to co-locate these services, these communicating services, onto cores of the same LLC domain because they share the last level cache, right? Whereas when you disable config SCHED MC, you're not even modeling the CCX. What you're really doing is, so if you see the diagram here, this is with config SCHED MC enabled, and the topology is going to be like you have a core, and on top of that, you have the MC domain, which is the group of cores which share the L3 cache, and then you have the die, which is basically the group of LLCs. So that is the ideal representation of the system. When you disable config SCHED MC, you get this kind of a flat representation where you just have the SMT and the die. And the critical thing is your SD share package resources, which determines what domain should be treated as your last level cache domain, is now the core here, right? It's really a small domain for you to play with. And so there is really no load balancing happening across cores of the cache domain because there is no notion of the L3 cache here. We've not even, with config MC equal to no, we have SCHED MC equal to no, we have even disabled that. And this kind of a configuration was giving a better result. So what was the reason? So when we looked at the data again, and this was probably to be anticipated because these tasks, this workload is really, all it's doing is waking up, doing something, and then handing the information to some other service, basically essentially waking that one up and going to sleep. So it is just wake up, run for a very short duration, sleep. Wake up, run for a very short duration, sleep. And it's waking each other up. That's the kind of workload that it is. And when you run with config SCHED MC equal to n, if you guys have seen the task wake up code, we try to find an idle. First of all, we try to see whether it has to be placed on the Waker's LLC or the previous LLC. And that's based on some heuristic like wake sync flag and WF sync flag. And really then what you do is you try to see if there is an idle core available. And with just one core, I don't know what are the odds that you'll find an idle core. So what we observed was most of the time the task would actually wake up on the previous CPU. That's what would happen. So essentially, you're doing the initial task placement properly where you're spreading it. And at every subsequent task wake up, you are just piling it onto the previous CPU. And that was giving you better results than trying to do this complicated thing of figuring out which LLC should I wake it up on, and then which core should I wake it up on, which thread on that core should I wake it up on, right? So, and in this particular case, auto scaling also increased the number of tasks for each service. And again, when we looked at is there any benefit it's gaining in terms of cache? Yes, it is. So it is seeing a 5% improvement in the total accesses per second. But if you see, most of the gains are from L2 and L2 or the L3 cache. So being there is really, really helpful, or waking up where it previously ran is really helpful for these kinds of tasks. So then we tried to mimic this particular behavior. We introduced sort of a hack called as a sticky wake up, which we say that, on wake up, I'm just going to wake you up on the previous core, right? I can probably explore the sibling SMT thread there, but it's just restricted to the previous core. And the other one was sticky LLC, previous LLC, where I'm just going to say, the target is the previous guy, and you are allowed to explore the full LLC. And what we observed was that the sticky previous LLC was able to reach very, very close to config SCHED MC equal to no, but still not there yet. Sticky previous score is bad in certain cases, like in the 2x case, it was not all that great, but sticky previous LLC was still giving us good results. So why? And like I mentioned, what on an average, how long do these tasks run? Right? It's somewhere between 50 and 100 microseconds. So they start, they run for 50 microseconds, and they go away. And in order to run this short task, you were actually expending so much time and energy to explore the whole domain to find an idle CPU. So question is it worth it? And this is where around the same time, Shenoy was working on the concept of short running tasks, identifying short running tasks so that you can wake them up on the waker. This was to optimize the run queue lock contention. This was from Intel. And what Abel Wu pointed out that, for certain workloads like Redis, because there's this short running and then they wake up and sleep, in very, very short durations, it probably may be useful to just wake them up on the previous core, right? Because the cache miss penalty is much higher than the potential gains they could accrue by waking up on an idle core. They really run for only so much.
Oh, so we have a similar issue with that on the OracleDB. So we have this polling issue because of you have networking interrupt coming on certain socket, because that's on Intel. Then because of because I presented LPC 2021, so you have a lot of interrupt coming, and our interrupt is mostly on that socket. So it's start polling all the tasks to the MC, to the socket. So what you want to is kind of spread the interrupt a little bit so they can spread the task evenly to different socket, or for your case, different LLC. So to better utilize the whole system.
Yeah, but
I know, because if you always go back to the previous CPU or previous LC, then the load balancing is done by the periodical load balancer, as well as the idle balancer.
And we looked at the load balancing stats, and the load balancer was finding nothing here, because these tasks run for such a short duration that by the time at the interval that you run periodic load balancer, by the time you decide you want to pull it, that task may have just.
So you're talking about them fighting each other?
Sorry?
The load balancing and the wake up fighting each other?
No, the load balancer is simply missing them.
Oh, because it's too short.
It's too short.
Okay.
Yeah, the original motivation behind latency nice was a very similar use case for OracleDB, where the query processing was such a short duration that it did not even make sense to look for an empty idle CPU on the MC domain.
Right. So yeah, maybe this is a similar issue here. I think Chris has a comment.
So one thing, and it's also related to the preemption topic from before too. One of the patches we want to talk about is we call it the shared wait queue patch, which basically, instead of trying to grab an idle CPU and hope it's still idle by the time you get started on it, we turn it into a pull mechanism where when the idle CPUs go idle, they say, hey, I'm going to take this task over here. And it reduces a lot of the races around defining what an idle CPU is. And it takes our idle percentage time down a step by one core, basically.
Okay.
It's related to all of this, right? So what we found was just the lower down we could get our idle time, the better all of these issues became.
And in your case, do you keep some list of idle CPUs that you can sort of ping and wake up so that they can pull, or how does that work?
No, they just pull from it a new idle balance. So it doesn't work well on multi-socket or multi-PTXs.
Okay.
So we're working on that.
So it's just when they go idle that they do this new idle balance. Okay, that's the issue that Libo and I were discussing yesterday. It's very, very similar.
Is it the CFS ceiling stuff? I'm not sure what you mean.
A few years ago, there was some patches that sounded exactly like that from someone from Oracle. I think it was CFS task setting. It was like, yeah, picking stuff on your idle. So I don't know if.
I'll hand it over. This is different, I think. This is Roman Gushin did this, and he wanted to upstream it, but he never did. And we're working on doing that like literally at this exact moment. So it sounds like somebody else knows what you're talking about there.
You can check the interrupts distribution. You can check the networking interrupt distribution, see if which core, which LLC those are.
Right.
So you can tell, okay, if it's the interrupt pulling, network interrupt pulling all this task in. So,
But that would be on the waker.
yeah, it is a waker. Waker
Yeah.
is the one pulling.
Yeah. But
So-
here is, I mean, the what we are seeing is we get the best results that when you wake the task, newly woken up task on the previous CPU. So the waker has very little.
Have like a better utilization if you
Yeah.
always go. Yeah, that's
Yeah.
the thing.
No, we don't have a better utilization when we pull him towards the waker.
Oh,
It's
because
the
of
other way
that.
around. Yes.
But what if you have better utilization?
We tried that. We don't get as much. In fact, it causes pile up.
Oh, that's interesting.
Yeah, it causes pile up. So in fact, we tried Shenoy's proposal, which was to pull one short running task onto the local thing and then probably spread
Okay.
the others.
So
Even-
that's the cache problem. So whether a weakened CPU or the previous CPU has the better cache, yeah, that's the problem because we don't know. The scheduler doesn't know.
No, we don't
There's
know.
no way they can tell. Yeah,
So
it's
yeah. So that's something to look for. But then the point is for such short running tasks, and if you know that there is a probability that the cache data is hot, where it previously ran, it makes sense to run there rather than.
It also has to do with the data, the semantic of data. So you're getting data from the networking. Some data you just we acknowledge there's something going on, then we process the data on the server on the previous socket. But sometimes we just want the data. The data is what we need, so we want to process on the waking CPU. So it's very hard to know which MC is better to go to. Yeah, for the scheduler.
So yeah, I mean, I don't know if there is I don't think there is a trivial way to make the scheduler cache footprint aware or something like that. I mean, we do have heuristics out there with things like WF sync, which give you a kind of a hint.
Yeah.
But apart from that,
Yes.
there's not much. So I'm going to skip this, and we tried out a few solutions because I mean, obviously we don't want to do the sticky wake up thing. It has to be a little bit more principled than that. So one approach that Prateek has tried out yesterday, and this is fresh off the oven. So what we were trying to see is like at every context switch, we sort of increment the ticket number of the task that is being of that particular run queue, and whichever is the task that is coming in, we sort of record that ticket number in the task struct. And when the task goes off to sleep, and eventually when it's being woken up, we try to see in its previous run queue, what is the current ticket number? How far is it? If there not too many tasks have been scheduled on that particular run queue, and it is a short task, then we just offload it there. So we need the short task heuristic, plus we need something like this, which tells you that recency. We could not use task hot because that requires us to take the run queue lock of the previous CPU, and we are not sure at this point in time whether we want to move there or not. It will be unnecessarily taking the lock and then saying, hey, this is not the right place, and leaving it. So we didn't want to go with that. And it is giving us some improvement. It is giving us fairly good improvement for the 8.8 LLC case. But the limit that we are maintaining currently for the ticket number is 8, which I think is a little high. So we have to still play with that, because currently the Hackbench is not very happy with these numbers. It's just showing significant regressions. Or probably we can just maintain an average sleep time and see if the average sleep time is smaller than the migration cost, which is kind of a proxy for task hotness without necessarily taking the run queue lock. So yeah, so these are things that we are currently looking at for this problem. But again, very short running tasks, escape the load balancer. We want to avoid this ping-ponging behavior. So yeah, that's really, I think.
Yeah, this is also an interesting problem for async runtimes. I mean, it's not really related to the kernel scheduler because this is more like a user space scheduler with fibers. But one kind of crazy thing we do at Meta is we'll sometimes wake like if we have a thread pool that's running async work items. If we think that we're going to be running a short work item soon, we'll actually wake a thread up and then just put it back to sleep so that the work item can get run on the task that's still busy doing other tasks. So yeah, I mean, this is like a common workload pattern.
This is the fibers. This is also similar to the fibers requirement, the UMCG requirement.
Yeah, so UMCG is like a little different because I mean it's similar, but they have a one-to-one relationship between threads and fibers. So in a more traditional async runtime where you have an end-to-end relationship, yeah, I mean essentially, but you're right actually, because for UMCG it's the exact same thing because it's the fiber doing the quick. It's the thread doing the quick.
And
quick
I think in that case, the hint was to always wake it up on the waker because we know that the waker is going away and handing off the baton or something like that.
Yeah.
So
yeah, this is a common problem that we need to solve for sure.
So yeah, any other thoughts? This is my last slide. Any other thoughts? Any other comments? Okay, I do want to call out a few people here. Special thanks to the workload team, Rohit and KVS and Akash for complying with us and being patient with us, running 100 different runs that we've asked them to run, collecting all sorts of statistics, helping us analyze this particular problem. So definitely thanks to them. And of course, thanks to Peter, Vincent, Shenoy, Abel, all of them who've contributed optimizations to the wake up and the load balancing path, which has made our life easier. I mean, we've been able to leverage the accrued benefit of all these things. And special thanks to Vincent. I think we would not have explored trying all these nice values and stuff unless if it had not been his suggestion. So at LPC last year, we had this discussion at lunchtime, and he suggested, why don't you go for latency nice? That did help, and that's where we said, okay, that's probably something that we should be doing here. So thanks to Vincent. Sponsored by AMD Legal. Thank you.